Welcome to the module Graph Theory. In today's session, we'll be discussing on the topic Introduction to Graph Theory and its applications. So let us begin the session with the history of graph theory, the terminologies, the topics of graph theory, the concepts and the different types of graph theory, and also the real life applications of graph theory. Let us begin the session with the history of graph theory. History of graph theory has its origin in the Euler's solution of Königsberg Bridge problem, which happened in the year 1736. So earlier, there was a Pregel river which was running or connecting two islands and the two river cities. And the problem which was earlier in that case is nothing but there were two islands linked to each other, and to the banks of the cities there was a river called Pregel river which connects the 7 bridges. And the problem in those days arises nothing but where a person has to start from one place or a city and they have to come back to the same city, crossing all the bridges exactly once. So this problem was being unsolved until Euler approached it. Now Euler created this as a graph model and proved that it is not possible. So he showed that any graphical model is going to be connected with respect to any real life situations where you construct some vertices and edges, and he proved that the problem doesn't have a solution. So he said that he generalized the problem and he developed a criterion for a given graph to be traversable if and only if each and every vertex is incident with an even number of edges. Now when I was explaining about the history of graph theory, here I was talking about the two important terminologies like vertices and the edges. So let me discuss about the edges and the vertices in the forthcoming slides. So the next development of graph theory came into existence in the year 1847, which was approached by Kirchhoff. In that year, he started solving the system of simultaneous linear equations, which gives the current in each branch and around each circuit of an electric circuit. So which means that any electric circuit or any electric network circuit can be given a graphical structure, and thereby you can find the solution for any electrical models. Now the next problem which came into existence in those days is nothing but Cayley, where he introduced an important concept called trees, and he studied the enumeration of isomers of the hydrocarbons with given number of carbon atoms. So as we all know that any ethane or methane is being connected by 4 hydrogen, whether it is going to be saturated or unsaturated, which can't be included in our graph theory. So here any chemical structure can be redrawn as a graph model, and thereby without much laborious experiments we can find the new molecules, and thereby we can find new medicines into the concepts. Now the next concept is going to be the graph theory. Another concept has been invented by William Hamilton in the year 1859. Now he coined a new problem or a game which is nothing but where he used a regular dodecahedron which introduces or which includes 20 vertices which are labeled with the names of the cities. And the player, so what was the challenge given to the player in those days is nothing but the player has to travel through all the cities or the circuits which will be like a closed circuit, and he has to cross all the edges which passes through each and every vertex exactly once. So the other side of the graph, the other side of the picture, you can see a graph has been given to it, and the graph has been, since it's been coined by Hamilton, we call that graph as an Hamiltonian graph. And since he introduced a new concept of graph theory called Hamiltonian circuit, and he also posed a solution for that problem also. And he gave another important idea that any number of Hamiltonian circuits in a complete graph on n vertices is going to have n minus 1 factorial by 2 different circuits are possible. So these are the important concepts which can be used in our real life. The next thing is going to be the definitions and the basic terminologies of graph theory. So any graph is going to consist of, as we all know that a graph is not going to be like a 2-dimensional figure or a graph paper. So here it is going to be in a different manner where you consist of a finite non-empty set vertices of G with respect to n vertices, which is going to be connected with respect to the edges of G. Now E of G is going to be nothing but unordered pairs of your vertices with nothing but distinct elements of your vertices. So here we have a small graph example where the vertex, it consists of 6 vertices and 9 edges are there. Now each and every vertices are connected by a line segment or a straight line, which we call it as edges under my graph theory, and those dotted lines are called as my vertices. So I have given some examples for graph theory which are nothing but train maps, social networks and the chemical models. So any train maps or any mapping structures or any networking or any transportation network can be mapped with your graph theory. So thereby thereby we can find the solutions or we can find the challenging answers for the challenging problems. The next thing is going to be the social networks, as we all come across different types of social media, gadgets and the informations. So here you can find the answers for such informations also. And the third information what I have given is chemical models. So any chemical molecular structures can be reframed or restructured as graph theory, thereby finding a new chemical structures and finding the answers which might make us more enormous changes in the chemical field or the industry. So the next thing is, next word, terminology which I have coined here is, a vertex can also be given a different nomenclature. Say for example, a vertex can also be called as a node or a junction, or some authors used to call it as a vertex, or even some people used to call it as zero cell or a zero simplex. Same way we can call an edge or a line segment by a different terminologies. For example, a branch or a line or an element or a one cell or even one simple arc or a simplex term. So all these are the different terminologies which can be coined for the vertex or the edges of a graph. So as I said, any graph is going to be based on two basic concepts, which is nothing but vertices and the edges. Now the next concept what I am going to discuss is order and the size of a graph. So the magnitude of graph is characterized by the number of vertices, which we call it as order of G, and the number of edges, which we call it as the size of G. So number of vertices and the number of edges, we call it as the order and size of a graph. Based on this, we study or we characterize the different types of graphs. As we characterize the different types of graphs, we try to find different solutions for the existing problems. And based on that, again another example is being coined by me here. So where I can correlate my graph into a different type of networking system. So as you can see that the green color highlighted things are nothing but different real life situations. Say for example, road maps, chemical molecules, electrical networks, social networks, linguistics, which is nothing but what we speak. A very famous concept of mathematics is nothing but automata theory, and even our web pages. All these can be coined in terms of my graph theory. So for example, if I choose road maps, the road maps is going to connect two different cities or the towns with the help of the roads. So here my towns are called as my nodes, and the roads connecting two cities or the towns is called as my edges. The same way, chemical molecules are going to be coined or converted in terms of a chemical structure, in a chemical graph structure, by using my atoms and chemical bonds. So the atoms are termed as my vertices and the chemical bonds are called as my edges. Same way I can go for directed and the undirected graphs. So what is meant by directed graphs? If there is a flow of direction known to us earlier to a problem, then we call them as a directed graph. So as I have coined here, a flow from one point to another point, where it can be left to right or right to left or clockwise or anti-clockwise, doesn't matter. So when we are able to give directions for any one point to another point, we call such graph as directed graph. So I have given some examples for the directed graphs also. For example, communications, circuits, mechanical, even in the field of financial and the transportation, we use my graph theory concepts. And there are some more concepts of the terminologies under my graph theory. To list a few among them, loops and the multiple edges. So what is meant by a loop? Some people used to call it as a self loop also, which means that a person can be a friend of himself. No, it is not possible. But here under my graph theory, we can say that a vertex can connect itself, and such idea we call them as a loop. So as the diagram says that a vertex is being started where it is being connected by an edge, again reaching the same point. So such diagram is called as my loop or a self loop. The next diagram or the concept is multiple edges or the parallel edges. So if two vertices or two or more vertices are connected by more than one edge, we call them as my parallel edges. So in this diagram we have all the concepts. Say for example, vertices are there, edges are there, multiple edges, as well as your loops are there. The next idea is going to be the directed and the undirected graph. So there are two different types, and one more information I have coined in this diagram is adjacent vertices. So what is meant by adjacent vertices? Adjacent vertex is nothing but, it's in a simple way I can say that I and the other person are friend enough. Myself and the other person are going to be friend if and only if there exists a friendly relationship between two people. Same way here also, if these two vertices are connected by an edge, we call those two vertices as adjacent vertices. If there is no friend of a person, person, then we call them as an isolated person. Same way here also we call that as an isolated vertex. There is another concept called multigraph. A graph which contains multiple edges and the no loops is called as a multigraph. So in the previous slide I was showing a diagram where there are multiple edges without loops. So that example is called as my multigraph example. And here there are edges which can also be called as multiple or parallel edges. So here there is a diagram where you have the edges are also going to be adjacent to one another. So when do we call two edges are adjacent to one another? If they share common vertices, we call them as an adjacent edges. And the next concept is going to be the pseudograph. Pseudograph is nothing but a graph which may contain multiple edges and loops is called as a pseudograph, and the vice versa of your multigraph. And the next thing is going to be the example where we have the multigraph concept as well as a pseudograph. So here there is a computer network which contains the loops as well as edges from a vertex to another vertex. So say for example here it connects different cities, San Francisco, Los Angeles and Denver, where the computer network system has been given, where you can see the multiple edges as well as the loops are being connected. So which is a real life example. And the other one is labeled graphs. So yet now we were discussing about the graphs where the vertices and the edges alone has been numbered. Yes, if you want you can change the names. Yes, as we give different names for a person, here also I can give different labeling for the vertices and edges, and such graphs are called as my labeled graphs. And again another type of graph is going to be the finite and the infinite. As the nomenclature says that if the number of vertices and edges are countable or finite in nature, we call such graphs as finite graphs. Otherwise we call them as an infinite. So as you can see that the first graph or the first example is a finite graph as it has 4 vertices and the 4 edges, whereas the second one which has been end rectangle with orange color, where you have infinite number of edges and infinite number of vertices. And again another example has been given by me in terms of directed graph. So directed graph is also been known as digraph. And again a same example is being given. The other one is the different types of graphs. So I have listed a few beginning stage of types of graphs. There are n number of types of graphs available under graph theory concepts, but here I have given the very basic fundamental things. Simple graph, multiple graph or multigraph, pseudograph, directed graph, and directed multigraph is being given here for the understanding purpose. Say for example, what is meant by empty graph? A graph which doesn't have edges at all. There might be such situations also, and in that case we call them as an empty graph. An empty graph on 0 nodes is called as a null graph. So can I call my empty graph as a null graph? Yes, empty graph can also be called as a null graph. There is a special name which we call it as a trivial case under mathematics. So what is meant by trivial? If we try to prove any results for an induction process with respect to n is equal to 1, we call them as a trivial case. So similarly under my graph theory also, if I am going to prove any results or any characterizations of a graph or properties of a graph with respect to n is equal to 1, say for example n is equal to 1 vertex, we call them as a trivial graph. Yes, so any graph which has only one vertex, we call it as a special name by singleton graph or a trivial graph. And the other side we have a weighted graph example. Weights are nothing but where if you want you can give a function or a weighting for the edges of the given graph. Say for example here 1, 2, 3, 4, 5, 6 are nothing but my vertices, and 1 and 2 are connected by a directed edge, 2 and 3 are being connected, 2 and 4 are connected, etc. It goes and on and on. But along with that you can see some more numbers like 1.2, 0.5, 0.2, 0.3. If there is a situation where you can find the weight or you can give some nomenclature for the weights of the given edges, then that particular graph is called as my weighted graph. Right. Now based on that we have several studies on a weighted graph, but we are studying only the basic part of it. The next important idea or the definition of a graph is going to be the degree of a vertex, which plays a vital role in the graph theory. The very first thing is degree of a vertex. So what is meant by degree of a vertex? The number of edges incident with a particular vertex is called as my degree of a vertex. So can a degree be 0? Yes, if a vertex doesn't possess any edges, then we call it as degree 0. If it is 1, which means that it is being connected with only other person or another vertex, then it is called as degree 1. If it is being connected, in the sense I am talking about the vertex, if a vertex is being connected with more than one vertex, say for example 2 vertices, then the degree becomes 2, 3, etc. It goes on and on. So based on the degrees, the very first fundamental theorem of graph theory came into place, which is nothing but the number of degrees of a vertices is nothing but twice the number of edges, which we call it as fundamental or the first theorem of graph theory. Now this paved the way for different theorems and the concepts to be proved under my graph theory. So here it is very visible in the graph itself. So here, say for example, in the first graph we have A, B, C, D, E, F, where you can find the degrees of each and every vertices and then try to sum it up, which is going to equal to the twice the number of edges. Again I am repeating it, summing up the degrees of each and every vertices is going to equalize the twice the number of edges, right. The next one is the topics of graph theory. So these are the very fundamental basic concepts or the emerging fields of topics or the concepts of graph theory. For example, domination, coloring of graphs, decomposition of graphs, network analysis, planarity, topological indices, which is related to my chemical graph theory, spectral graph theory, graph labeling, etc. It goes on and on. These are the different topics where the graph theory concepts is been emerging and it has been developing slowly in day-to-day life. The very first application of graph what I am going to discuss is nothing but the graph coloring problem. As I showed in the previous slide, the different topics of graph, very important one is nothing but the graph coloring situation. So that graph coloring situation can be applied in a very different cases. I have chosen a very fundamental thing, say for example, making schedule or an exam timetable for a college or for an university. So what was the condition given? Suppose we want to make an exam schedule for an university where we have been given different subjects and different students are enrolled in every subject. Many subjects would have common students. So which means that the students might have a common, provided the students might also have a backlogs. So you have to see to that the scheduling has to be done in a very proper way such that the common students are not to be given two subjects in the same time. At the same time, how many minimum time slots are needed to schedule all exams? Now this kind of problem can also be approached graph theory concepts. So this problem can be represented as a graph where every vertex is nothing but a subject and an edge between two vertices is nothing but where there is a common student. If a student has got two subjects, then the person has to be connected or those two subjects has to be connected by an edge. In a similar way, what happens? The entire solution or the entire situation can be picturized as a graph problem. Based on that, you can use a coloring concepts and try to get the answers. So here the second question answer can be given by using the chromatic number of the graph. Chromatic number is nothing but what is the minimum coloring needed to find the coloring of the graph, and based on that we can find the answer for the second question given in this real life situation. Same way I can use my coloring concepts for mobile radio frequency assignment. When frequencies are assigned to different towers where the different towers will have a different frequencies. Now in that situation what happens? Frequencies will be assigned to all towers at the same location, provided you have to assign the frequencies in such a way that what will be the frequency to be allotted and what is the minimum frequency needed to make the situation in a error-free manner. So again the problem can be taken forward using my graph coloring conditions and you can find the answers. So this problem is also an instance of a graph coloring problem where every tower represents a vertex and an edge between two towers represents that they are in the range of each other. If there is a range between those two towers, we will be connecting by an edge, otherwise we never connected. Hence you can find the solution. In the same way, I can use my graph coloring concepts for clustering, data mining, image capturing, even in the image segmentation it can be used. So these are the real life situations of graph coloring. The next application of graph theory is going to be the traveling salesman problem. So those who have studied optimization techniques would have come across a concept called traveling salesman problem. So what was the problem? Again, this also arises in the earlier centuries, not in the present situations. So there is a problem or there is a poster for a contest run by Procter & Gamble, P&G in 1962. The situation is nothing but where the problem has been given to the traveling salesman persons. They have to visit all the 33 cities, start from their particular city. Say for example, they will start in a one city and that city we call it as a home city. They have to traverse through all the other cities assigned to them, again return back to the starting point itself without traversing the others only once. So such situations we call it as my traveling salesman problem. Again this condition can also be taken forward or it can be picturized using my graph theory concepts and try to find the answers. The next theorem is going to be, the next application is going to be the four color conjunction. States that any map in the plane can be colored with 4 or lesser than colors. Now again four coloring problem, as I said in the earlier case, this idea will be useful for finding the solutions for any real life situations. The next one is how does Google works. Say for example, as we all Google the different datas or informations from the Google, we start in browsing it. When we start browsing, what happens? Each page is considered as a node according to my graph theorist, and two pages are joined by an edge if there is a link from one page to another. If you start choosing for a data, different pages comes into place. Now two pages are connected if the datas or the informations are matches with each other. If the datas or the informations are matching, we join them by an edge. So again, what happens? That real life situation can be mapped with my networking, graph networking. Now again, there are fundamental algorithms or the very famous algorithms under my graph theory to solve such problems. So immediately we call them as my Google's page ranking algorithm. So here, what is the idea of the page ranking algorithm is nothing but the more links a page has pointing to it, the more important it is. So as we start browsing different ideas, what will happen? It points different informations. So the more you choose a particular page, automatically what happens? It will be given more preferences, and based on that, what happens? If an important page links to your page, this is worth more than the unimportant page. Automatically this will highlighted in the beginning stage. So this kind of information or page ranking will be done using the graph theory algorithm. Again, what happens? So here I have chosen an example. So here the colored balls represents that how far are we using a particular thing. Say for example, A, B, C, D, E, F are nothing but different web pages. The one which has been often highlighted or often googled by us will be given the maximum percentage. So here B is been browsed very frequently, so it has been given a maximum percentage, and the next lesser is being given to C, etc. It goes on and on. So again, this can be correlated with respect to graph theory, and whatever is a problem arise with respect to that situation, you can approach or you can apply that particular graph theory concepts and try to find the answers. So here, same for example, same way I can use it for any kind of social networking, even for making a recommendation. Say for example, recommendation plays a vital role under my e-commerce. Say for example, everyone knows about Amazon, where the Amazon always gives preferences for the suggestions. When we start buying any product in an Amazon, immediately it will show us buy this product or get this suggestion will be given to us. Now again, what is the need for using that suggestions? As the suggestion is being given to us, we started browsing that particular product. So automatically what happens? How it gets connected? Again, the graph theory concept has been related to it. So again, the page ranking system has been adopted. When I say page ranking, behind the page ranking we have a graph theory algorithm to solve such conditions. These are the real life situations where we use our graph theory concepts. Again, another important concept where my graph theory is being applied is in the field of chemistry. So any graph theory, any chemical molecules can be restructured as graph theory concepts, and thereby what is the main usage of giving this chemical structure in terms of graph theory concept is without laborious experiments or much involvement or much money is going to be spent over that, we can find new ideas, thereby finding new medicines. Say for example, like COVID and all, we can find new medicines without much laborious experiments or any other informations. So such informations or such conclusions can be drawn very easily using this graph theory ideas. The next implication is going to be even in the field of psychologists. So how the psychologists will be using is, say for example, the regions where they will be using in terms of lifespan of an individual. So the lifespan of an individual is going to be my vertex. Again, it is going to be connected with my planarity concepts. Even in the social network, as I said in the previous slides, if two vertices are connected by the points and the interpersonal relation by edges, yes, you can draw like a graphical structures. The very important concept is going to be the Markovian process, which is again a probability theory. Even in the concept of Markovian process, my graph theory is being used to find the answers. Whether the suggestion, whether the situation is going to be favorable or unfavorable, whether it is going to give a positive answer or a negative answer, all those informations can be studied using this Markovian process. So as I said, the next one is graph theory. Hence, graph theory is an incredibly important part of modern daily life, as I showed in my previous slides, and it also gives a solution to single graph theory problem which have many real world applications. So when I solve a single problem using my graph theory, it is ultimately going to be used in many more real world applications. Hence, problems in graph theory can be worth than a lot of money. Thank you. Thanks a lot.